The winds of Mars howl across a silent world. Red dust drifts over canyons that once echoed with the sound of flowing water. Ancient riverbeds stretch like fossilized arteries across a dying planet, their channels carved by torrents that roared billions of years ago. No rivers run here now, no rain falls from the butterscotch sky, no oceans shimmer beneath the pale, distant sun. But once, long before human eyes ever looked skyward with wonder, Mars was blue. It had valleys filled with rushing rivers, lakes that mirrored crimson skies, and storms that carved continents with the patient persistence of water. Deltas spread like ancient hands where mighty rivers met vast seas. Ice caps gleamed at the poles, and underground aquifers fed springs that bubbled with life-giving water. Today, only the scars remain, dried channels that snake across hemisphere-wide landscapes, frozen deltas preserved in stone, and the ghostly outlines of vanished seas whose shores still trace phantom coastlines visible from orbit. The planet has become its own museum, displaying the relics of a hydrological civilization that lasted longer than life has existed on Earth. Tonight, we'll journey across time itself, to the age when Mars was alive, when water sculpted its surface with the same artistic precision that shaped the Grand Canyon and carved the Norwegian fjords, when perhaps, just perhaps, microscopic life stirred in its mineral-rich rivers, beginning evolutionary experiments that we may never fully understand. Before we begin, I'd love to know something from you. Out of all the mysteries of space, what fascinates you the most? Is it ancient worlds like Mars, where entire civilizations of water once existed? The birth of galaxies in cosmic nurseries billions of light years away? Or the strange physics that bind reality together? Dark matter, quantum entanglement, the very fabric of space-time at sea. Share your thoughts in the comments. I always read them, and your curiosity helps shape what we explore next. Every comment becomes a guiding star for future journeys into the unknown. And if you enjoy these deep journeys through science and time, consider subscribing. Every new subscriber becomes part of this growing constellation of thinkers, explorers of the unseen universe who understand that wonder is not just an emotion, but a way of seeing the cosmos. Now, let's return to Mars. Let's uncover the world it once was, and perhaps the one it might yet become again. We open on modern Mars, a world of desolation and haunting beauty. The landscape stretches endlessly, painted in shades of rust and amber. Dust devils dance across plains that haven't felt rain in 3 billion years. The atmosphere whispers with winds so thin they could never lift a feather, yet somehow manage to create storms that engulf the entire planet for months at a time. But through the eyes of our orbital satellites, through radar that penetrates stone and spectrometers that taste ancient chemistry, we see patterns beneath the dust. They emerge like invisible ink under heat, ancient riverbeds branching like the circulatory system of a giant drainage networks that once channeled the lifeblood of a world. These aren't simple scratches in the rock. They're complex dendritic systems, river networks that mirror the Amazon basin, the Mississippi Delta, the great waterways of Earth. Some channels stretch for thousands of kilometers, winding through crater fields and volcanic plains with the unmistakable signature of liquid flow. The Mars Reconnaissance Orbiter has mapped over 15,000 kilometers of these ancient riverbeds, more than enough to stretch from New York to Tokyo and back again. Scientists recently discovered networks in regions where many believed there wasn't any evidence for water, hidden river systems that suggest Mars was far wetter than we ever imagined. Royal Astronomical Society. From our orbital vantage point, we can trace these ghostly waterways across an entire hemisphere. They converge toward the northern lowlands, toward the Great Basin that once held an ocean covering nearly a third of the planet. Deltas fan out like ancient river mouths, their sedimentary fingers reaching into what was once a vast sea. We imagine the sound of Martian rain, perhaps lighter than Earth's downpours due to the thinner atmosphere, but persistent enough to carve these monumental channels. We envision the shimmer of countless lakes under a fainter sun, their surfaces rippling with waves that lapped against shores of volcanic glass and sedimentary stone. Billions of years ago, Mars was not a frozen desert. It was a world of water, a blue marble suspended in the void, perhaps glowing with the same ethereal beauty that Earth displays to astronauts today. And then, silence. The rivers disappeared, the lakes evaporated, the oceans fled to space. But the land remembers. In every canyon, every dried channel, every preserved delta, Mars tells the story of its lost youth, a time when water flowed freely and life, perhaps, first stirred in cosmic waters far from home. 4.5 billion years ago, the solar system was a crucible of creation. Mars formed amid cosmic chaos, volcanic eruptions that could dwarf Yellowstone, meteoric bombardments that liquefied entire continents, and a newborn sun whose radiation carved away early atmospheres like a cosmic wind. The young planet was a hell world of molten rock and poisonous gases, seemingly destined for eternal sterility. But beneath its tormented crust, something extraordinary was happening. Water vapor, delivered by comets and asteroid impacts, began to condense in the cooling atmosphere. The first Martian clouds formed, wispy and tentative, but real. And with them came the first precipitation in the history of Mars. Picture that moment. The first raindrops falling on an alien world. They hissed against volcanic rock, carved tiny channels in cooling lava, and pooled in the lowest places to form the first Martian lakes. These weren't the gentle spring rains of Earth, but torrential downpours from an atmosphere thick with water vapor and volcanic gases. As the bombardment era ended and the surface cooled, these early rains became more persistent. Seasons formed, perhaps not as regular as Earth's, but cycles of warming and cooling that drove weather patterns across the planet. Rivers began to flow, cutting their first tentative channels through the young Martian landscape. Valles Marineris, now a canyon system stretching over 4,000 kilometers and reaching depths of 7 kilometers, began as a series of fractures in the planet's crust. But water found these weaknesses and exploited them, widening cracks into channels, channels into rivers, and rivers into the greatest canyon system in the solar system. Recent geological analysis suggests that groundwater flow played a crucial role, with aquifers feeding water to the canyon system from below, while surface rivers carved it from above. NASA. The early Martian hydrological cycle was violent and beautiful. Volcanic activity heated underground water reserves, creating geysers and hot springs that may have provided the perfect conditions for life's first tentative experiments. Mineral-rich waters dissolved elements from the rock: sulfur, iron, magnesium, calcium, creating chemical soups that could support metabolism. In these warm, chemical-rich streams beneath a crimson dawn, life may have begun its second experiment in our solar system. Microscopic organisms, perhaps chemosynthetic bacteria that fed on the planet's volcanic energy, could have thrived in these early waters. They would have been simple, single-celled pioneers, but pioneers nonetheless, the first inhabitants of an alien world. The Martian day was shorter then, spinning faster on its axis. The seasons were different, driven by a more active climate system. And most importantly, the atmosphere was thicker, perhaps dense enough to support liquid water at the surface, warm enough to prevent rivers from freezing solid during the long winter months. For hundreds of millions of years, Mars experienced its golden age of water. Rivers flowed continuously, feeding into vast lake systems that covered much of the northern hemisphere. Deltas formed and reformed as water levels rose and fell with the cycles of climate and volcanic activity. This was Mars in its youth, a water world, a potential nursery for life, a planet that might have developed its own unique biosphere if circumstances had been just slightly different. The seeds of an alien ecosystem were planted in those early waters, experiments in biology that we're only now beginning to understand through the chemical sigh. Natures preserved in Martian rocks. But this aqueous paradise was fragile, dependent on a complex balance of atmospheric pressure, volcanic activity, and solar heating. And slowly, inexorably, that balance began to shift. Not all rivers flow gently. Some roar with the voice of gods. Mars experienced catastrophic floods that dwarf any natural disaster in human history. Immense torrents that could have filled the Mediterranean Sea in a matter of days. These weren't gradual river floods, but sudden, apocalyptic deluges that reshaped entire continents and carved canyons in hours that erosion usually requires millions of years to create. The evidence lies scattered across the Martian surface, like the aftermath of a cosmic flood myth made real. Massive outflow channels, some wider than the English Channel, snake across the landscape, their floors scoured smooth by torrents of unimaginable power. Teardrop-shaped islands, some the size of Manhattan, stand as monuments to the incredible forces that once rushed past them. These floods had several possible origins, each more dramatic than the last. Underground ice reservoirs, heated by volcanic activity, could suddenly melt and burst to the surface like planetary-scale geysers. Asteroid impacts might have punctured subsurface aquifers, releasing millions of years of stored groundwater in catastrophic outbursts. Or perhaps massive glacial dams, built up over centuries, suddenly failed and released entire frozen seas in matters of hours. The largest of these floods carved the Kreis-Planitia outflow channels, wounds in the planet that remain visible from orbit 3 billion years later. NASA's orbital surveys have found flow patterns, hydraulic jumps, and sediment deposits that tell the story of water moving at speeds approaching 100 kilometers per hour, carrying boulders the size of buildings and carving canyons 100 meters deep in solid rock. Imagine standing on ancient Mars as these walls of water, hundreds of meters high, race across the plains. The ground would shake with their approach, a rumbling that could be felt hundreds of kilometers away. The sky would fill with spray and vapor as billions of tons of water crashed over escarpments and carved new valleys in real time. In places, these floods moved so much material that they actually changed the planet's topography, creating new basins and filling old ones with sediment layers that are still visible today. The floodwaters carried more than just rock and debris. They transported dissolved minerals, organic compounds, and potentially microscopic life forms across vast distances. A microbe that evolved in a volcanic hot spring could suddenly find itself carried thousands of kilometers away to a completely different environment, seeding life across the planet in a process of biological dispersal that would have taken millions of years through normal river flow. Recent analysis by the Mars Reconnaissance Orbiter has revealed that some of these flood channels show evidence of multiple episodes, suggesting that these catastrophic events happened repeatedly over Mars' history. Each flood would have dramatically altered the planet's geography, creating new lakes, filling old ones, and potentially triggering climate changes that could last for millennia. The sediment layers left by these floods are geological treasures. They preserve chemical snapshots of ancient Martian environments, capturing the precise mineral composition of the water, the temperature at which it flowed, and potentially even biosignatures, chemical evidence of life that was carried along with the flood debris. But perhaps most remarkably, these floods created some of the most potentially habitable environments in Martian history. The mixing of different water sources, the transportation of nutrients across vast distances, and the creation of new lake systems provided unprecedented opportunities for life to diversify and spread. If Mars ever had a truly global biosphere, it may have been distributed and connected by these magnificent, terrible floods. The scale of these events challenges our imagination. The largest Martian floods moved more water in a few days than the Amazon River carries in a century. They carved features that are visible from space, created landscapes that persist billions of years later, and may have been the primary mechanism by which life, if it existed, spread across the planet. These were the agents of both creation and destruction on ancient Mars, forces that could obliterate entire ecosystems in hours, but also create new habitable environments and connect previously isolated biological communities. They represent the awesome power of water to shape not just landscapes, but the very possibility of life on an alien world. At its peak, Mars may have held more water than the Mediterranean Sea, Arctic Ocean, and Gulf of Mexico combined. An ancient ocean, perhaps 1.6 kilometers deep on average, stretched across the northern hemisphere of Mars, covering nearly 20% of the planet's surface in a vast alien sea. From orbit, we can still trace its ghostly shorelines, subtle changes in elevation, different rock types, and sedimentary deposits that mark where waves once lapped against Martian beaches billions of years ago. This wasn't just a large lake, but a true ocean, large enough to have its own weather systems, deep enough to remain liquid even as the planet began to cool, and complex enough to potentially support an entire ecosystem of microscopic life. Recent geological evidence suggests the presence of ancient deltas with long backwater zones, a technical term that provides some of the strongest proof yet that large rivers once flowed continuously into this northern ocean. Phys.org, the ocean's existence is written in the rocks. Orbital surveys have identified specific types of minerals that only form in the presence of standing water, clays that require long-term hydration, sulfates that precipitate from evaporating seas, and carbonates that form when carbon dioxide dissolves in large bodies of water. These aren't trace amounts, but vast deposits that suggest the ocean persisted for millions or even hundreds of millions of years. More tantalizingly, we've found salt deposits, not just any salts, but the specific types and distributions that suggest tidal action, seasonal changes, and the complex chemistry of a living ocean. Some areas show layered evaporite deposits, suggesting that the ocean went through cycles of expansion and contraction, possibly due to climate changes or seasonal variations. The shorelines themselves tell a story of dynamic change. In some places, we see evidence of violent wave action, rocky beaches where storms pounded the coast with fury equal to Earth's most powerful hurricanes. In others, we find gentle, sloping shores where sediments accumulated peacefully over geological time, creating vast tidal flats that may have been ideal nurseries for early life. But this ocean was not static. It was connected to a global hydrological system that included rivers, lakes, underground aquifers, and atmospheric water vapor. Rivers fed the ocean from the south, massive drainage systems that channeled water from the entire southern hemisphere into this northern sea. Some of these river systems were larger than the Amazon, carrying not just water, but sediments, minerals, and potentially organic compounds from across the planet. The ocean also had its own climate. Computer models suggest it could have supported its own weather patterns, evaporation from the surface creating clouds that rained back onto the sea and the surrounding land, creating a regional water cycle that may have persisted even as other parts of Mars began to dry out. Seasonal ice formation at the poles could have driven currents and mixing that distributed nutrients and maintained the ocean's chemical balance. Most remarkably, this ocean existed during what geologists call the Late Heavy Bombardment, a period when asteroids and comets were still regularly hitting the planets. Each impact that struck the ocean would have vaporized vast amounts of water, temporarily thickening the atmosphere and creating planet-wide rainstorms. In a sense, the ocean was constantly being replenished and stirred by cosmic impacts, creating a dynamic, ever-changing environment. But the ocean didn't simply vanish overnight. It retreated gradually, leaving behind a series of smaller lakes and inland seas that persisted for millions of years after the main ocean disappeared. We can trace this retreat in the geological record, layers of sediment that mark different water levels, salt deposits that show where the last remnants evaporated away, and finally, the wind-blown dust that covered the empty basin. The death of the Martian ocean was a slow tragedy that played out over geological time. As the atmosphere thinned and the planet cooled, the ocean began to freeze and sublimate, turning directly from ice to vapor and escaping to space. Solar radiation, no longer blocked by a protective magnetic field, broke apart water molecules in the upper atmosphere, allowing hydrogen to escape and leaving behind the oxygen that now rusts the planet's surface. Today, that ancient ocean floor is a frozen desert, covered by dunes and dust storms. But beneath the surface, geological surveys suggest that water ice, the frozen remnants of that ancient sea, may still exist in vast underground reservoirs. Recent studies have detected what could be liquid water reservoirs deep beneath the northern plains, remnants of the ocean that once covered this region. UC Berkeley. The Martian Ocean represents one of the greatest tragedies in planetary history, a world ocean that could have rivaled Earth's seas in its potential for supporting life, lost to the vacuum of space over the course of geological time. But it also represents hope. If Mars once had oceans, it could potentially have them again. For water to exist on the surface of any world, that planet must hold its breath. It must wrap itself in a blanket of atmosphere thick enough to keep water liquid, warm enough to prevent universal freezing, and stable enough to persist across geological time. Early Mars had such an atmosphere, perhaps 10 to 100 times thicker than today's wispy shroud, rich in carbon dioxide and water vapor, possibly containing methane and other greenhouse gases that kept the planet warm, despite receiving only 43% of the sunlight that bathes Earth. But atmospheres are fragile things, especially on small planets orbiting active stars. Mars began losing its protective breath almost from the moment it finished forming. The culprit was magnetic, or rather, the lack thereof. Earth's magnetic field, generated by the churning of molten iron in our planet's core, creates an invisible shield that deflects most of the solar wind, the stream of charged particles constantly flowing from the sun. Mars had such a magnetic field once, generated by its own molten core, but as the planet cooled, its magnetic dynamo shut down. Without magnetic protection, the solar wind began the slow work of atmospheric erosion. High-energy particles struck the upper atmosphere directly, imparting enough energy to atmospheric molecules to allow them to escape to space. This process, called atmospheric sputtering, continues today. NASA's MAVEN mission has directly observed the Martian atmosphere bleeding away at a rate of about 100 grams per second. Over geological time, this adds up to the loss of an entire Earth-like atmosphere. The loss wasn't uniform or steady. During periods of high solar activity, solar storms, and coronal mass ejections, the rate of atmospheric loss increased dramatically. The young sun was more active than today's relatively calm star, producing more powerful solar storms that could strip away vast quantities of Martian air in just days or weeks. As the atmosphere thinned, a cascade of climate changes began. The greenhouse effect weakened, allowing more heat to escape to space. Surface pressure dropped, lowering the boiling point of water and making it impossible for liquid water to exist except in the deepest valleys. The water cycle slowed, then stopped, as there was no longer enough atmospheric pressure to support the evaporation-condensation cycle that drives weather. But the atmosphere didn't just disappear, it transformed. Much of the carbon dioxide that once warmed the planet became trapped in the polar ice caps and absorbed into the regolith, the layer of dust and broken rock that covers the Martian surface. Some water vapor condensed into underground ice deposits. The atmosphere became a repository, storing the remnants of Mars' former climate in frozen form. The transition from a thick, watery atmosphere to today's thin, dry air happened over hundreds of millions of years, a gradual fade rather than a sudden collapse. During this transition period, Mars experienced what scientists call the semi-arid to arid transition, a time when liquid water became increasingly rare but didn't disappear entirely. Recent atmospheric modeling suggests this transition wasn't smooth. Mars may have experienced multiple episodes of atmospheric thickening and thinning, possibly driven by massive volcanic eruptions that temporarily replenished the atmosphere, or by changes in the planet's orbital characteristics that affected how much sunlight it received. During these episodes, rivers may have flowed again, briefly by geological standards, but long enough to carve some of the younger channel systems we observe today. Some Martian valleys show evidence, of multiple episodes of water flow separated by long dry periods, suggesting that the planet's climate flickered between habitable and inhospitable conditions multiple times during its history. The pale orange sky we see today, tinted by iron oxide dust suspended in the thin air, is a ghost of its former self. The atmospheric pressure at the Martian surface is less than 1% of Earth's, equivalent to the air pressure at an altitude of 35 kilometers above Earth. It's so thin that liquid water immediately boils at the surface temperature, turning to vapor and escaping to space. But even today's tenuous atmosphere tells a story. Trace gases like methane, detected in tiny quantities by orbital spectrometers and rovers, suggest that Mars may still be geologically or even biologically active. The methane doesn't last long in the Martian atmosphere. It should be destroyed by solar radiation within a few hundred years, so its presence suggests an ongoing source, either geological processes in the subsurface or possibly even microbial life. The story of Mars's lost atmosphere is ultimately a story about planetary evolution and the delicate balance required to maintain a habitable world. It shows us how a planet with flowing rivers and vast oceans can gradually transform into a frozen desert, and it raises profound questions about the long-term stability of Earth's own atmosphere and climate. Yet there's hope in this story of atmospheric loss. If Mars once had a thick atmosphere capable of supporting liquid water, then perhaps it could have one again. The atmosphere didn't disappear completely. Much of it is still there, trapped in ice caps and absorbed into the soil. The question isn't whether Mars can be made habitable again, but whether we have the will and wisdom to restore what time and space have taken away. Though Mars appears dead from space, the planet guards its secrets well. Beneath the dusty surface that gives Mars its ruddy complexion lies a hidden cryosphere, a vast network of frozen water that rivals the ice sheets of Antarctica. This subsurface ice isn't just scattered deposits, but enormous reservoirs that stretch for thousands of kilometers beneath the polar regions, mid-latitudes, and even, surprisingly, near the equator. Recent breakthroughs in ground-penetrating radar have revolutionized our understanding of Martian water ice. The European Space Agency's Mars Express mission has detected what appear to be layers of water ice stretching several kilometers below ground, representing more water than has ever been found in this part of the planet. These aren't small patches, but continent-sized deposits that could contain more water than some of Earth's largest lakes. European Space Agency, but the most tantalizing discovery may be liquid water, not frozen, but flowing in briny reservoirs far below the surface. Scientists have found evidence of a massive underground reservoir system located 10 to 20 kilometers beneath the Martian surface that may contain more liquid water than was ever present in the ancient Martian oceans. This water exists in the pore spaces of rocks, kept liquid by pressure, geothermal heat, and high concentrations of dissolved salts. UC Berkeley. The implications are staggering. If confirmed, these deep reservoirs represent not just water, but potentially habitable environments that have persisted for billions of years, shielded from the harsh surface conditions that make Mars appear lifeless. In these dark, salty chambers, protected from radiation and temperature extremes, microbial life could theoretically not just survive, but thrive. The subsurface ice tells the story of Mars's climatic history. Different layers represent different epochs, periods when the planet's orbit brought it closer to or farther from the sun, times when the axis tilted differently and changed the patterns of seasonal heating and cooling. These ice layers are like tree rings, preserving atmospheric gases, dust, and potentially even organic compounds from different periods in Martian history. Some of the most interesting ice deposits are found in the mid-latitudes, where orbital images reveal strange, lobate features that look remarkably like glaciers. These viscous flow features show clear signs of ice flow, similar to glaciers on Earth, but they're covered by a protective layer of dust and debris that has preserved them for millions of years. When meteorite impacts occasionally punch through this protective covering, they reveal pure water ice beneath, sometimes creating crater floors that shine brilliant blue in orbital photographs. The discovery of equatorial ice has been particularly surprising. Traditional climate models suggested that water ice should be unstable at low latitudes on Mars, sublimating away over relatively short geological timescales. But the detection of extensive ice deposits near the equator suggests either that these deposits are much younger than expected, or that they're protected by mechanisms we don't yet fully understand. Underground ice on Mars isn't static. Seasonal changes in temperature cause the ice to expand and contract, creating polygonal patterns on the surface similar to those found in Earth's permafrost regions. These patterns are particularly visible in high-resolution orbital images of the Martian Arctic, where the ground is literally cracking and reforming due to the freeze-thaw cycle of subsurface ice. The presence of extensive subsurface ice has profound implications for future human exploration of Mars. Water is essential not just for drinking, but for producing rocket fuel, generating oxygen, and supporting agriculture. The discovery that much of Mars is essentially a giant ice reservoir covered by dust means that future missions may have access to water resources almost anywhere they land. But accessing these ice reserves presents significant challenges. The deepest liquid water reservoirs are far beyond the reach of current drilling technology. Even the shallower ice deposits are often meters below the surface, requiring specialized equipment to extract. The ice is also contaminated with perchlorates, toxic chemicals that are common in Martian soil, making purification a necessity for any human use. Recent studies have also suggested that the subsurface ice on Mars may be dynamic, with active processes that move water between different reservoirs. Geothermal activity, pressure changes, and even tidal forces from Mars' two small moons may drive complex flows of water and ice deep beneath the surface, creating an active hydrological system that we're only beginning to understand. Perhaps most intriguingly, some scientists believe that the interaction between liquid water and rock in these deep reservoirs could create the chemical conditions necessary for life. The breakdown of water molecules by radioactive decay could produce hydrogen, which serves as an energy source for certain types of bacteria. The high pressure and temperature could drive chemical reactions that create organic compounds, and the vast timescales involved, billions of years of stable conditions, would provide ample opportunity for life to evolve and adapt. Mars, it seems, is not entirely dead. It's merely sleeping, its life-giving water hidden beneath a deceptive surface of dust and desolation. The planet that once flowed with rivers and oceans hasn't lost its water. It has simply buried it, storing it in a vast underground reservoir that may harbor the greatest biological treasures in the solar system. In the permafrost of Mars lie the memories of ancient rivers, the potential for future life, and perhaps even the seeds of worlds yet to come. In September 2024, NASA made an announcement that sent ripples through the scientific community. The Perseverance rover had discovered what NASA called the closest we have ever come to discovering ancient life on Mars. The discovery came from a rock nicknamed Chayava Falls, found in the Neretva Vallis, an ancient river valley that was carved by water rushing into Jezero crater billions of years ago. The rock is unlike anything previously found on Mars, covered in distinctive leopard spots and containing white veins of calcium sulfate that provide clear evidence that water once flowed through the rock itself. NASA. But Chayava Falls is just the latest in a growing catalog of tantalizing clues that suggest Mars may once have been inhabited by microscopic life. The evidence doesn't come from dramatic fossils or obvious biological structures, but from subtle chemical signatures, mysterious rock formations, and patterns in the geology that whisper of biological processes. Jezero crater, where Perseverance has been exploring since 2021, was once a lake basin fed by rivers that created a delta, a fan-shaped deposit of sediments where the river met the lake. These sedimentary layers, now exposed and accessible to the rover's instruments, preserve a detailed record of the environmental conditions when the lake existed 3.5 billion years ago. Recent research has revealed that Jezero experienced multiple episodes of habitability, with complex cycles of water, mineral formation, and organic chemistry that could have supported microbial life. Rice University, the rover has found organic molecules, carbon-based compounds that are the building blocks of life as we know it. While organic molecules can form through non-biological processes, the specific types and concentrations found in Jezero suggest that biological processes may have been involved. Some samples show organic compounds associated with minerals that form in the presence of water, suggesting that if life existed, it was intimately connected with the aquatic environment. Perhaps most intriguingly, Perseverance has discovered mineral patterns that are eerily familiar to geobiologists who study ancient life on Earth. Layered sedimentary structures, chemical gradients, and mineral deposits that mirror those created by microbial communities in Earth's early oceans. These biosignatures don't prove that life existed, but they show that the conditions were not just suitable for life, but potentially optimized for it. The Curiosity rover, exploring Gale Crater since 2012, has made its own contributions to this growing body of evidence. The rover has found evidence of ancient lakes too. Hat persisted for millions of years, long enough for life to evolve and establish complex ecosystems. Chemical analysis of rocks from these ancient lake beds shows sulfur isotope ratios that some scientists interpret as evidence of biological sulfur cycling, a process performed by certain types of bacteria. More recently, Curiosity discovered evidence of ancient stream beds with flowing water that persisted long enough to transport sediments over considerable distances. The rover found rounded pebbles and sedimentary structures that could only have formed through prolonged water flow, exactly the kind of stable, long-term aquatic environment where life could have thrived. But the search for life on Mars extends beyond these flagship missions. Orbital observations have revealed seasonal changes in atmospheric methane concentrations that some scientists believe could indicate ongoing biological activity. Methane on Mars is particularly intriguing because it's quickly destroyed by the planet's chemistry, meaning that any methane detected must have been produced recently, within the last few hundred years. The seasonal pattern of methane release is especially fascinating. Concentrations appear to peak during Martian summer and decline during winter, similar to patterns we see on Earth where biological activity increases with temperature. While geological processes could also explain methane release, the seasonal pattern suggests a more dynamic source that responds to environmental changes. Recent advances in analytical techniques have allowed scientists to study Martian meteorites, rocks blasted off Mars by asteroid impacts and eventually landing on Earth, with unprecedented precision. Some of these meteorites contain complex organic compounds, mineral structures that resemble fossilized bacteria, and chemical signatures that suggest water-rock interactions under conditions that could support life. One particularly intriguing meteorite, designated ALH84001, contains microscopic structures that some scientists believe could be fossilized Martian bacteria. While this interpretation remains controversial, the meteorite definitely contains organic compounds and mineral formations that require the presence of liquid water to form. The cumulative weight of this evidence doesn't prove that life existed on Mars, but it demonstrates that the planet had all the necessary ingredients: liquid water, organic compounds, energy sources, and stable environments that persisted for hundreds of millions of years. If life ever arose on Mars, it would likely have been microscopic, possibly similar to the extremophile bacteria that thrive in Earth's most challenging environments. But here's what makes the search for Martian life so compelling. If we find evidence of past or present life on Mars, it would suggest that life is not unique to Earth. Since Mars and Earth formed from the same primordial material and experienced similar early conditions, the emergence of life on both worlds would imply that biology is not a rare cosmic accident, but a natural consequence of planetary evolution. The rock samples collected by Perseverance are currently stored in sealed containers on the Martian surface, waiting for a future sample return mission that will bring them back to Earth for detailed analysis in our most advanced laboratories. These samples may hold definitive answers to one of humanity's most profound questions. Are we alone in the universe? The answer may be written in the stones of Mars, in the chemical signatures preserved in ancient river sediments, in the microscopic structures that formed when the red planet was blue. We stand on the threshold of potentially discovering that life has arisen at least twice in our solar system, and if twice here, then perhaps countless times throughout the cosmos. Mars may not just be a planet that once had water, it may be a world that once lived, breathed, and evolved, a biological experiment that paralleled Earth's own journey from sterile rock to living world. And in its ancient rivers, we may find the proof that life is not an accident, but an inevitability. Humanity's gaze now turns toward Mars with an ambition that would have seemed impossible just decades ago: the restoration of a world. The dream of terraforming, transforming Mars back into a planet capable of supporting liquid water and possibly even life, has evolved from science fiction fantasy to serious scientific inquiry. Recent breakthroughs in atmospheric engineering, climate modeling, and our understanding of Mars's hidden water reserves have made the prospect of planetary restoration not just conceivable, but potentially achievable within centuries rather than millennia. The challenge is monumental, but not insurmountable. Mars still contains most of the water that once flowed in its ancient rivers. It's simply locked away in ice caps, subsurface reservoirs, and mineral deposits. The atmosphere that once kept the planet warm enough for liquid water is mostly still there, frozen in the polar caps and absorbed into the regolith. What Mars needs is not the creation of an atmosphere and hydrosphere from nothing, but the restoration of what already exists in dormant form. Recent research has proposed several innovative approaches to warming Mars and restoring its atmosphere. Scientists at the University of Chicago and other institutions have developed models for using engineered nanoparticles, microscopic dust made from materials already present in the Martian atmosphere, to enhance the greenhouse effect. By releasing carefully designed particles into the upper atmosphere, it might be possible to trap more solar heat and begin a process of gradual warming. University of Chicago. The process would begin slowly. Nanoparticles made from graphene or aluminum, produced from Martian atmospheric CO2 through electrolysis, could be released at a rate of just a few liters per second. These particles would act like microscopic mirrors, trapping heat and potentially doubling Mars's greenhouse effect, raising global temperatures by 5 degrees Celsius, enough to begin melting subsurface ice and releasing water vapor into the atmosphere. Science advances. As temperatures rise, a positive feedback cycle could begin. Melting ice would release water vapor, which is itself a greenhouse gas. Carbon dioxide frozen in the polar caps would sublimate, thickening the atmosphere and further warming the planet. Eventually, the atmospheric pressure might increase enough to allow liquid water to exist at the surface. Not everywhere, but in the deepest valleys and basins where pressure is highest. The first restored Martian rivers might flow in valles marineris, where the elevation is lowest and atmospheric pressure would be highest. Water released from melting subsurface ice could collect in the canyon system, creating the first liquid water bodies Mars has seen in billions of years. These initial water bodies would be small, perhaps seasonal, and certainly not capable of supporting complex life, but they would represent the first step in a process of planetary resurrection. Advanced terraforming scenarios envision more dramatic interventions. Redirecting comets or asteroids to impact Mars could deliver both water and energy, potentially jump-starting the atmospheric restoration process. Orbital mirrors could focus additional sunlight on the polar ice caps, accelerating the release of frozen CO2 and water. Genetically engineered organisms, perhaps based on extremophile bacteria that already exist on Earth, could be introduced to begin producing oxygen through photosynthesis. But terraforming Mars raises profound ethical and practical questions. Do we have the right to fundamentally alter an entire planet? What if Mars currently harbors indigenous life that could be threatened by atmospheric changes? How do we ensure that terraforming benefits all of humanity rather than just the wealthy nations or individuals capable of reaching Mars? There's also the question of timescales. Even the most optimistic terraforming scenarios require centuries or millennia to achieve meaningful results. The nanoparticle approach might begin showing effects within decades, but creating an atmosphere thick enough to support unprotected human life would take much longer. Future generations would inherit a project begun by their ancestors, working toward a goal they themselves might never see completed. Perhaps more achievable in the near term is para-terraforming, creating enclosed, habitable spaces rather than transforming the entire planet. Large domed cities or underground habitats could maintain Earth-like atmospheres and temperatures while the rest of the planet remains in its current state. These enclosed ecosystems could include artificial rivers, lakes, and even small seas, creating Earth-like environments within protective barriers. The technology for para-terraforming already exists in rudimentary form. The International Space Station demonstrates that humans can maintain closed-loop life support systems for extended periods. Biosphere 2 and similar projects have shown that self-contained ecosystems can function, albeit with significant challenges. Advances in materials science, renewable energy, and closed-loop agriculture are making large-scale enclosed habitats increasingly feasible. But the ultimate goal remains full terraforming, the restoration of Mars to something resembling its ancient state. Computer models suggest that a terraformed Mars might not look exactly like Earth, but it could support a unique ecosystem adapted to lower gravity, higher radiation levels, and a different day-night cycle. The planet might have its own distinctive climate patterns, seasonal cycles, and perhaps even indigenous life forms that evolve from introduced Earth organisms. Imagine standing on the rim of Valles Marineris 1,000 years from now, watching morning mist rise from a river flowing through the canyon floor. The sky might still have a reddish tint from iron oxide dust, but it would be thick enough to breathe, warm enough for liquid water, and dynamic enough to support weather systems. Clouds would form over the restored northern ocean, bringing seasonal rains to continents where rivers could flow once again. This restored Mars would be neither Earth nor the ancient Mars that existed billions of years ago, but something new, a hybrid world that combines the best aspects of both, shaped by human ingenuity and natural processes working in concert. It would represent humanity's greatest act of environmental restoration, the healing of a world that time and cosmic forces had broken. Whether terraforming Mars is ultimately possible remains an open question. The technical challenges are immense, the timescales are daunting, and the ethical implications are complex. But the fact that serious scientists are now studying detailed proposals for planetary restoration shows how far our understanding of Mars has progressed. We now know that Mars was once a water world, that it still contains vast reserves of H2O, and that its atmosphere could theoretically be restored. The rivers of Mars may flow again, not as ghosts of an ancient past, but as harbingers of a reborn future. As we reach the end of our journey through Mars' aqueous history, we must confront what this story tells us about our own world and our place in the cosmos. Mars stands as both promise and warning, a reminder that worlds can be born blue and die red, that water is both the giver and taker of life, and that the difference between a living planet and a dead one can be measured in the strength of a magnetic field or the thickness of an atmosphere. The planet that once flowed with rivers teaches us that habitability is fragile. Earth's climate system, which we often take for granted, depends on a delicate balance of atmospheric gases, ocean currents, volcanic activity, and solar radiation. Mars shows us what happens when that balance shifts, slowly at first, then inexorably, until rivers become memories carved in stone. But Mars also demonstrates the resilience of water and the persistence of hope. Despite losing its atmosphere and surface water billions of years ago, the planet has preserved vast reserves of H2O in hidden reservoirs. The same geological processes that stripped away the ancient oceans also created the underground ice deposits that could support future life. In losing its rivers, Mars may have saved the seeds of their eventual return. The search for life on Mars has revealed how intimately biology and geology are connected. The same processes that create habitable environments, water-rock interactions, chemical cycling, energy gradients, also preserve the evidence of life long after organisms have disappeared. Every rover mission, every orbital survey, every analysis of Martian meteorites adds to our understanding of how life and planets co-evolve. Recent discoveries have suggested that Mars may have been habitable for much longer than previously thought. Rather than a brief, early wet period followed by rapid desiccation, Mars may have experienced multiple episodes of habitability spanning hundreds of millions of years. This extended timeline vastly increases the chances that life could have emerged and evolved, potentially reaching levels of complexity we haven't yet imagined. The implications extend far beyond Mars itself. If life arose independently on both Earth and Mars, two planets formed from the same stellar disk around the same star. It suggests that biology is not a cosmic accident, but a natural consequence of planetary evolution. The universe may be teeming with life, much of it arising in the primordial oceans of worlds we haven't yet discovered. Current astronomical surveys have identified thousands of exoplanets, many of them potentially habitable worlds orbiting distant stars. Some of these planets may be experiencing their own Martian transitions right now, losing their atmospheres and surface water as their parent stars evolve or their magnetic fields weaken. Others may be in their Earth-like phase, with active water cycles and potentially thriving biospheres. The study of Mars has also revealed the importance of planetary protection, both protecting other worlds from contamination by Earth life and protecting Earth from potential alien organisms. As we prepare to bring Martian samples back to our planet, we must carefully consider the possibility that Mars harbors its own indigenous life forms that could be threatened by terrestrial organisms or that could pose unknown risks to Earth's biosphere. But perhaps the most profound lesson from Mars is about the nature of time and change. The rivers that once flowed on Mars existed for longer than complex life has existed on Earth. Entire ecosystems may have risen and fallen on the red planet before the first eukaryotic cell appeared in Earth's oceans. The geological timescales involved challenge our human perception of permanence and change. What seems eternal to us, our climate, our oceans, our atmosphere, is actually dynamic and constantly evolving. Earth is currently in the midst of its own atmospheric transition, driven by human activity rather than natural processes, but potentially just as significant as the changes that transformed Mars. The study of Mars provides crucial insights into how planetary atmospheres respond to changing conditions, and what factors determine whether worlds remain habitable. The future of Mars remains unwritten. Current missions are collecting data that will inform our understanding for decades to come. The samples collected by Perseverance may provide definitive evidence of past life, answering one of humanity's most fundamental questions. Future missions may detect current biological activity in the planet's subsurface environments, and beyond scientific discovery lies the possibility of restoration. The same technological capabilities that allow us to study Mars could eventually allow us to restore it. The planet that taught us about the fragility of worlds could become a testament to our ability to heal them. Mars could transition from a cautionary tale to a success story, a world reborn through the marriage of natural processes and human ingenuity. The ancient rivers of Mars flow now only in our imagination, but they may not remain imaginary forever. In the vast subsurface reservoirs, in the polar ice caps, in the very rocks and atmosphere of the red planet, the materials for restoration await. What was lost to time and space could be reclaimed by knowledge and will. Mars mirrors Earth, not just in its past, but potentially in its future. Both worlds began as water-rich planets capable of supporting life. One thrived and became a garden, the other withered and became a desert. But endings are not always final, and death is not always permanent. In the cosmos, what ends can begin again, what dies can be reborn, and what flows can flow once more. The story of Mars's ancient rivers It's ultimately a story about the persistence of hope in a universe that seems designed to crush it. Despite billions of years of cosmic violence, despite the loss of atmosphere and the freezing of oceans, despite the apparent death of an entire world, the possibility of restoration endures. Water remembers how to flow, atmospheres remember how to breathe, and planets remember how to live. In learning to read the story written in Martian stone, we've discovered that no ending is truly final. The rivers that once flowed on Mars are not gone, they're waiting. And perhaps, in learning their ancient songs, we can teach them to sing again. As our journey across the ancient rivers of Mars comes to an end, we're left with a profound truth. Water is the universe's most persistent dreamer. In every ice crystal locked beneath Martian permafrost, in every mineral vein carved by vanished streams, in every delta preserved in stone, water tells the same story: that life finds a way, that worlds can be reborn, and that nothing in the cosmos ever truly ends. The rivers of Mars may be silent now, but they are not forgotten. In the laboratories where scientists analyze Martian samples, in the computer models that simulate ancient climates, in the hearts of explorers who dream of distant worlds, those ancient waters flow still. Every time we look up at that rusty point of light in our night sky, we're seeing not just a planet, but a promise. A promise that what was lost can be found, that what died can live again, and that the universe, for all its apparent hostility to life, remembers every river it has ever held. The waters of Mars are calling to us across the void, not with the voice of the dead, but with the song of the waiting. They're waiting for us to understand their story, to learn from their loss, to perhaps someday restore what time has taken away. And when that day comes, when human footprints first mark the shores of restored Martian seas, when the first drops of engineered rain fall on soil that has been dry for 3 billion years, when rivers flow once again through valleys that have known only silence, we will understand that we haven't conquered Mars. We will have remembered it back to life. The grand rivers on Mars were never truly lost. They were simply sleeping, dreaming of the day when water would dance once more beneath alien skies, when life would stir again in cosmic waters, and when two worlds would share the same blue dreams. That day may come sooner than we think. The universe, after all, remembers water, and water always finds a way home. Thank you for joining me on this journey across time and space, through the ancient rivers of a world that once was and might yet be again. If this exploration has stirred your sense of wonder, remember to subscribe and share your thoughts in the comments. The cosmos is vast, filled with mysteries waiting to be discovered, and your curiosity helps guide our next adventure into the unknown. Until next time, keep looking up. And remember that every world has its story, every planet its poetry, and every river its song.